Hi everyone, I hope you are doing well. So in today's video, I'll be going through the 2019 chemistry exam multiple choice section. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah, let's smash through this video. Question 1. An understanding of Le Chatelier's principle is useful in the chemical industry. The prediction that can be made by using this principle is the effect of what? Okay, first let's actually understand what Le Chatelier's principle is. Let's see what Le Chatelier's principle is. If you guys don't know what it is it's pretty much a principle that states that when a system is subjected to a change, for example, you increase volume, increase pressure, decrease temperature, increase the concentration of reactants or product, and which, it disrupts the equilibrium, the system will try to move to partially oppose that change. That's what it does. So it goes back to it wants to go back and fix that change. And so whenever you look at Le Chatelier's principle, it's all about equilibrium position. It's all about equilibrium. Equilibrium position with change. That is the change of, concentration, all the other stuff. So that's what it is. So let's look at the answers. The prediction that can be made using this principle is the effect of catalysts on the rate of reaction. Okay, catalysts do increase the rate of reaction, but that's not what Le Chatelier's principle is. It talks all about equilibrium position. It has nothing to do with rate of reaction, so that's the problem with this one. Catalysts on the position of equilibrium. Okay, now it's saying position of equilibrium, that's perfect, but catalysts do not have an effect on the position of equilibrium, as we know. Next one. Changes in temperature. Yes, changes in temperature is with change, like you change temperature, change volume. On the rate of reaction, absolutely not. Rate of reaction is not Le Chatelier's principle. It's all about equilibrium position. And so D, changes in the concentration. Great, that's a change of reactants on the position of equilibrium position. Beautiful. So D would be the best here. Question 2. The thermochemical equation for the complete combustion of glucose is what? So here we're talking about complete combustion. Now, what do we know about complete combustion? We know that the products are going to be CO2 and H2O. That's it. And we also know about combustion is that the enthalpy change is negative. Okay, so for all of them, they're all negative, so that's not quite helpful. But let's look at the product. There has to be CO2, H2O. This one has CO2 and H2O. This one has CO. CO is carbon monoxide. So this here, we would consider as incomplete combustion. So not B. C. Okay, this here is the fermentation. If you don't know, this is the fermentation of glucose, which creates actually bioethanol. So that's not a complete combustion. It's not a combustion reaction, as what we're saying. It's actually a fermentation reaction. And D is, that's absolutely wrong. It doesn't have, CO2 or H2O. So A would be the best here. Absolutely. It reacts with oxygen and it creates CO2 and H2O. Beautiful. An easy question, actually. Question 3. A compound has the following skeletal formula. The molar mass of this compound is what? Okay, nice and easy. So what we're going to do is first, let's draw in its structural formula. So how many carbons? So there's a carbon here. Goes with this carbon, and there's a double bond of oxygen here and here and here. Beautiful. And I'm gonna write all these hydrogens here. Oh, what am I doing? That's not gonna be there. Yep. Hydrogen here, here, here. All these hydrogens, and done. Does that look good? 1, 2, 3, 4, 5. Yes. So how many carbons do we have? We know the molar mass of one carbon is 12. We have 5. How many hydrogen? We know the molar mass of hydrogen is 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. And lastly, how many oxygens? Just 1. So it's 16. Easy. Let's use our calculator and calculate that. So 12 times 5 plus 1 times 10 plus 16. And that gives me 86. So D is your answer. Easy. Question 4. Oxidative rancidity can be slowed down by adding what? So first let's understand what oxidative rancidity is. It's pretty much like it's like a chemical reaction. It's like the series of chemical reactions that pretty much deteriorate fats and oils, pretty much triglycerides, and it results in those foods having this unpleasant odor and taste. For example, like let's say you take meat and you put it in heat. You don't actually put it in the freezer, but you leave it in the heat. And it starts to smell. It gets that's what oxidative rancidity is. So again, and there's many ways we can actually slow down oxidative rancidity. That is, we put in a cold, we decrease temperature. For example, when you take meat and you put it in a freezer, that slows down oxidative rancidity as we are decreasing heat. Light is a problem. Be careful. For example, when you're actually putting say in your freezer, you put meat, and so when you open the fridge, the light turns on, and when you close it, you can see the light turning off. It's because light is actual energy. So when you're putting light, it actually increases oxidative rancidity. So that's why when you close down your fridge, it actually closes that light. So it slows down oxidative rancidity, and it's also cold down there. So it also more slows it down. So that's oxidative rancidity. And really, let's really look at how oxidative rancidity actually occurs. So we know that triglycerides have fatty acids, and these fatty acids have double bonds. Some of them actually have double bonds. And the problem with double bonds is they are very reactive with oxygen. And if they react with oxygen, there's going to be an oxidation reaction, and this reaction actually creates both some ketones and some aldehydes. And that's a problem. These are the ones that kind of make that ugly smell. And so it's all about that double bond. That's the problem. If we could, some fatty acids don't actually have that double bond, so they're much slower down in terms of oxidative rancidity. So let's look at the options. Oxidative rancidity can be slowed down by adding heat. No, heating just, increases oxidative rancidity. As we said, we want to make sure we get in low temperatures so they don't go bad. Ultraviolet light, again, violet light is a problem. It just, increases oxidative rancidity. Sodium ions, what? Don't even know, actually. I'm going to put a question mark on that. What do sodium ions got to do with that? And a reducing agent. Okay. I forgot. We need to also talk about, there's other ways we can decrease oxidative rancidity, and that's called using antioxidants. And what are antioxidants? They pretty much interrupt the propagation of free radicals by being actually preferably oxidized in preference of oxygen. So how oxygen is being oxidized with those fatty acids? If we can take something like an antioxidant that can give its electrons, we want to give those electrons. Give it its electrons. And so oxygen doesn't actually react, and so these two react, and hence we don't actually form these ketones and aldehydes. So antioxidants are a great way. And so a reducing agent, which is the one that's going to be that oxidizes, is what? The one that oxidized. What do we know about oxidation? We know oxidation is the loss of electrons. So it gives out electron, and that's what we need. If we can, this here, a reducing agent is pretty much, in this case, it's in terms of oxidative rancidity, it's actually a antioxidant, and that's a great way to slow down oxidative rancidity. So absolutely D would be the best in this case. Sodium ions, I still don't know. I have no idea about, but I know reducing agent perfectly, because again, free radicals, we want to make sure we give out electrons, and so in preference, we want to give electrons so the oxygen doesn't react with that double bond. Perfect. So let's look at question 5. At the start of the day, a student sets up a galvanic cell using 2 electrodes, nickel and metal X. This setup is shown in the diagram below. Okay. Alright. Consider the following alternative metals that could be used to replace metal X. Okay, so we have zinc, lead, cadmium, copper. At the end of the day, the student checked the color of the solution in half cell 1, okay, and observed that the solution is a darker green, okay. Which of the following alternative metals could cause the color of half cell 1 to become darker green? So let's think. If this cell here is darker green, what do we know? That the solution has a lot of Ni2, like nickel 2 plus ions. The more it has, the more darker the solution is. So how's the reaction going to go? Well, if we want to produce, so what's happening is pretty much there's the production of nickel ions pretty much. And the only way we can actually get the production of nickel ions is nickel solid goes to nickel I2 plus 2E minus here. Because these are in our product side in this half cell reaction. And hence we are producing more nickel ions in this part here. So as we can see, it is an oxidation reaction. Hence, this half cell actually goes through oxidation. Then, hence, this one must go through reduction. All right. And the way this actually gives a lot of hints, because if I know that this is the reduction, what do we know? We know that the reduction, like the reduction reaction, it's always higher than the oxidation reaction. So what I can do is I can go to my data booklet here and have a look at the electrochemical series. Where is nickel? So nickel, let's look over nickel. Nickel's over here. For this reaction to occur, we know that the one that goes through reduction must be higher than that nickel. So let's look at zinc. Nope, zinc is lower. That's not right. Lead, let's see. Yes, lead is higher than nickel in the electrochemical series. Hence, this reaction will go like this, and hence we're going to produce nickel 2 plus ions. Great. So lead works. What about cadmium? Nope, cadmium is below. And what about copper? Copper is great because it's also up more than nickel. So 2 and 4 are the ones, metal 2 and 4 pretty much. So metals 2 so B is your answer for that one. Easy. Not too bad. Question 6. Which of the following statements about enzymes is correct? The induced fit model suggests that the shape of an enzyme remains constant throughout the catalyzed reaction. So first, let's really understand what the induced fit model is. So let's say we have a enzyme that has an active site like this, something like this. And say we have a substrate, like a square. This is your substrate. And this is your enzyme. So what happens is we want the substrate to fit in that active site. The problem is, look at the shape. That's not the perfect shape. But the induced fit model suggests that when it can actually fit in there, because what the enzyme's active site does is it kind of changes its shape to fit that substrate. For example, when this goes in there, it will actually look like this then. It will change its shape, its active site. So for the substrate to fit in that active site. So that's what the induced fit model is. So the question says, the induced fit model suggests that the shape of an enzyme remains constant for what the... No, it doesn't remain constant. We can see that the active site, the actual enzyme changes shape. The active site's enzyme changes shape, so that's rubbish. Enzymes may have their tertiary structure altered during a catalyzed reaction. Yes, looks like that, because you can see that the structure is actually altered. So I'll put a tick on this. Could be that one. Enzymes can catalyze more reactions over a broad range of rubbish. Be careful. We know that enzymes are very susceptible to denaturations, and denaturation occurs because of pH and temperature. Remember, enzymes have this narrow range of temperature, both, and pH. If you increase the pH by a little or the temperature by a little, it will denature. So we know for a fact enzymes can catalyze most reactions over a narrow, not a broad. D. Enzymes may change the equilibrium constant of... No, you know that enzymes does not have any effect on the equilibrium constant, so rubbish. B is your answer. Question 7. A molten mixture of equal parts of aluminium fluoride and sodium chloride undergo electrolysis. Which of the following statements about this reaction is correct? So sodium metal will be produced at the cathode and fluorine gas will be produced at the anode. So let's actually look at our electrochemical series and actually start predicting what's going to happen. Let's look at this. We have L3 plus, fluorine minus. For this, we have Na plus, Cl minus. All right? And let's highlight those in our electrochemical series. So Al plus is over here. Right, though, fluorine minus is over here. Na plus is over here, and Cl minus is over here. So let's look at the strongest reducing one, or the strongest oxidant. It's the ones always on the left side of the electrochemical, and it's the highest. In this case, it would be aluminium, because we're going up on the left side, and this is the highest. So aluminium will, again, reduce and create aluminium solids. So we're going to actually have aluminium solid. And where does that occur? Because it's on the left side of the... and it's been reduced, it means it occurs at the cathode. Easy. Done. What about our strongest oxidation, or the strongest reductant? We know the strongest reductant is always downwards. It's the strongest by going downwards on the right side, which in this case, it's this one. And it will form chlorine gas. So chlorine gas will form on the anode. Easy. That's it. Let's put that back. All right. So sodium metal. A and B say talk about sodium metal. There's no sodium metal being produced. It's only chlorine gas and aluminium. C says aluminium metal will be produced at the cathode. Great. And chlorine gas will be produced at the anode. Beautiful. C is your answer. Question 8. Consider the following statements about galvanic cells and fuel cells. Let's use a different color here. Question statement 1. The overall reaction is an exothermic reaction. That is true. By the way, if you don't know, galvanic cells and fuel cells are pretty much just galvanic cells. So they pretty much have the same function. They convert chemical energy to electrical energy. And yeah, they have quite a lot of similarities pretty much. But there are some little differences that will come by. So for a galvanic cell and a fuel cell, because it's converting chemical reactions to electrical energy, it is an exothermic reaction because, again, it's not like 100% all the chemical energy is being converted all to electrical. There are some heat produced. And how is heat produced? We know that exothermic reactions release heat. So absolutely, galvanic cells and fuel cells, the overall reaction should be exothermic for all of them. So easy. 1 is pretty much correct. 2, electrons are consumed at the negative electrode. I have no idea. Let's look at this. Okay, so we know for a galvanic cell, we have the negative and we have the positive. And we know always that the electrons go through negative to positive for a galvanic cell and both fuel cells. And so the question tells electrons are consumed at the negative. No, they are consumed at the positive electrode. So 2 is wrong. 3, both the reducing agents and the oxidizing agents are stored in each half cell. Wrong. They are stored separately. Be careful with that. They are not stored both in a half cell. So that's good. 4, the electrodes are in contact with their reactants and the electrolyte. So let's let's have a look at a galvanic cell. So for example, a galvanic cell, this is your electrolyte. Okay, so, and this is your electrode. Now, okay, the electrode is in contact with the electrolyte. That's great. And yes, the reactants are in contact with the electrodes. So that's good. But what about a fuel cell? Now, I have no idea. Let's just draw a fuel cell here. So fuel cell looks like this. And has these 2 electrodes that are okay. Yeah, so this is where your electrolyte is in the middle. And so the electrodes are in contact with the reactant. That's true. And the electrolyte. Yes, actually, because remember, it is porous. So they have these little small holes. And yes, so they are pretty much in contact with this electrolyte. Yeah, I just fully forgot about porous. But yeah, they are porous. They have these little holes so they gases can pass through. And yes, they are pretty much in contact with that electrolyte. So 4 looks good. All right, let's look at 5. The production of electricity requires the electrodes to be replaced regularly. Yeah, for galvanic cells, that's true because, like, for example, galvanic cells is when a reaction goes, sometimes those electrodes can, break down, they decompose, and so that's a problem. So they probably do want to be replaced regularly, but be careful. For fuel cells, the electrodes are inert. So they probably get, replaced rarely because they don't actually react. So it's it's quite sometimes useless to replace regularly. So yeah, I would say for galvanic cell, absolutely, but for fuel cell, I wouldn't say that's correct. So, yeah, I would say 5 is also wrong. Which of the following sets of statements is correct for both galvanic cells and fuel cells? Easy. 1 and 4 pretty much. So choose B. I'm still thinking about 5. Is it 1, 4, and 5? No, there isn't. There's no option 1, 4. Because this one here is, I want to make sure I'm 100% correct with that. Yeah, there's no statement, so it's only B probably. Done. Question 9. A reaction has the energy profile diagram is shown below. Which of the following represents the energy profile for the reverse reaction? So when you're drawing the reverse reaction, it's pretty much the most easiest. So imagine drawing an axis here and just kind of reflecting this along the enthalpy change axis. So it look like this, this, and this. So that's what it looks. So initially, well, the forward reaction is actually exothermic. So, and it was what? What was the enthalpy change? It's exothermic and it's -10. And so we know that when we reverse a reaction, the enthalpy change is going to be positive now. So, and as you can see, it is positive in our case too, as we've drawn. So, the final, okay, so change in hand will be positive, so we can exclude those. Final product energy. So, okay, let's look at our thing. So our product energy is over here, our final product energy, as we can see. And it is what? It is 50 to 100. So it's 50. So B is your answer. What an easy, beautiful question. Now, a lot of students should realize that this is a kind of a typical question in exams. So the way I would not I want to show you how it looks, but normally what you do is like, for example, if this is exothermic, you know, because it's exothermic, you know that a reverse will be endothermic, so it will always be +10. And for the reverse, it's always going to be, this is actually, for the forward reaction, this is the final reactant energy. And so the final reactant energy for the reverse will be the actual final product energy. So this here will be this final product. Nice and easy. Question 10. Which of the following statements about coenzymes is correct? So if you don't know what first coenzymes are pretty much these small organic molecules that attach to the active site of an enzyme. But let me actually show you what it actually looks like. And what it does is pretty much, let me just continue. So it changes that surface shape to enable the substrate to bind. So for example, let's have a look at this. What can I, okay, so if I have a draw at this, nice draw, like that, like this. So we draw this enzyme. And so this is a coenzyme. It's like a rectangle in this case. And this is our substrate, this square. So this again is our sub. This here is our coen. And this here is our enzyme. All right. So what it does is the coenzyme actually goes inside the enzyme. It binds to the active site of the enzyme and actually makes a beautiful place for the substrate to fit in. Because if the substrate was just without the coenzyme, this substrate if it goes in there, there'll be this empty space, and hence the active site is not fitted and the reaction won't go on. So that's what a coenzyme does. It just kind of like, it positions itself on the surface shape and enables the substrate to bind pretty much. So let's look at question 10. Which of the following statements about coenzymes is correct? Coenzymes alter the secondary structure of enzymes. Rubbish. Be careful with that. They're not altering. They're just binding there. In other words, they're just facilitating the reaction. They're just binding there only for the substrate to fit in. They're not changing any structure of the enzyme. It's not like the induced fit model so it just fits perfectly in there, and whereas the the substrate fits in perfectly. Be careful. It does not change the secondary structure. It doesn't even change the structure of the enzyme itself. It's not the induced fit model here. B. Coenzymes can react with enzymes to produce proteins. Wait, coenzymes can react with enzymes. That's rubbish. Look, you cannot have... Okay, coenzymes don't react. That's the first thing. They only facilitate the reaction. For example, so... That's rubbish. And in other words, these are just saying that if you take a coenzyme and you react it with an actual enzyme, we produce proteins. Now, we know that both enzymes and coenzymes are like made out, enzymes are made of proteins, but reacting them together does not produce proteins. They only facilitate, and they're not very, they don't react. Be careful. Coenzymes don't react, they only facilitate other reactions. C. Coenzymes can bind to enzymes to make a reaction occur. This is the best definition. Yes, coenzymes bind to the enzyme to make the reaction occur. Easy. So I'll put a tick on that one. The tertiary structure of coenzymes prevents them from binding. They do bind with the enzyme, so that's quite rubbish. So C is your answer for that one. Let's have a look at question 11. 5 milliliters of ethanol undergoes combustion in a test tube with a diameter of 1 centimeter. This equipment is performed in a fume cupboard. Okay. The temperature in the fume cupboard is 20 degrees Celsius. Whichever following actions will reduce the rate of reaction. Whenever we're talking about the rate of reaction, it's all talking about collisions. How fast are the things colliding? If they're colliding quick, then there's a high rate of reaction. If they're low and slow, it's a slow rate of reaction. So let's look at A. Mix 2 milliliters of dilute solution of sodium hydroxide with ethanol. Okay, we know already that ethanol is a weak acid. This one here is a weak acid. And so if you're like diluting it with NaOH, which is a strong base, you're decreasing the concentration of ethanol, and hence what? If you decrease the concentration, we know we're decreasing the collisions and hence decreasing the rate of reaction. So I would say I'll put a tick on that. So that's good. That does reduce the rate, decrease the rate of reaction. B. Perform the experiment in a test tube with a diameter of 2 centimeters. Let's look at this. So if we have a test tube, let's say this is the 1 centimeter one, and say we have, I don't know, like the same 5 milliliters of methanol. So these are your reactants. And so because it's a combustion reaction, it's going to release heat. It releases heat. And so let's say it takes, I don't know, 2 seconds and it fully releases the heat. Hence the, it's finished the reaction. Remember, rate of reaction is how quickly the reaction goes. Like quickly, yeah. And so if you have like double the size and you still had this, so it would be less because it's still the same 5 milliliters of ethanol, what would happen? It will quickly release. It will quickly, because there's more surface area on top of this thing. So like all that heat, it's just going to release quicker because there's more area, like there's more for it to flow out. And hence it will probably like take half a second pretty much for the reaction to complete. So the quickest one in this case would be, if you, increase the diameter, the rate of reaction does increase. So that's wrong. Let's have a look at C. I want to rub this out. Increase the temperature in the fume cupboard to 25. No, if you increase the cupboard, you're increasing the rate of reaction. You're increasing the collisions, the velocity of the collisions, the molecules, and hence increasing that rate of reactions. Easy. D. Increase the volume of ethanol to 7 milliliters. If you're increasing the volume of ethanol, so you're putting actually more ethanol. In other words, you're just like increasing the concentration. Hence, if you're increasing the concentration, you are increasing the rate of reaction. So that's also wrong. A just looks the most suitable. In this question, so pick that one. Easy. So let's look at the next questions. 12. A compound has the molecular formula this. Okay. Which type of chemical analysis would be the most useful in determining whether the compound has a stereoisomer? So let's first define what a stereoisomer. Pretty much, stereoisomer is an isomer with the same order of atoms but different spatial orientations. That's what an isomer is. A stereoisomer, my apologies. And let's really look at the classes, because a lot of students do get confused with the classes. So isomers, there are 2 classes of isomers. They go between what we call structural isomers. It's the one that you would have learned in like year 11. It's just pretty much the same atoms, but just different structures. They're different rearrangements. And then we have stereo isomers. Oh my god, I struggle with this spelling. And so that's the 2 classes. But stereoisomers actually goes more beyond that, because they go for another 2 classes. And so one class is geometric. And geometric is the ones like, the cis and trans, where it deals with double bonds. And the last one is actually enantiomers. I don't even know how to spell that, but I think it's like this. Or we can actually just call them optical isomers. And it's the one with the the chirality of carbon. So a carbon atom that has different side groups. So yeah, so when we're talking about stereoisomers, we're talking about this over here, this field over here. And so because, of course, geometric is useless because we're not dealing with double bonds here. This is just, you can straight away draw this structure. It's not. We're dealing with enantiomers and optical isomers, and these are the ones that are going to be dealing with like the chirality of carbon. We want the carbon to be chiral. So let me rub that out now. So, okay, mass spectrometry. Now, mass spectrometry is quite useful because it just tells us about the fragments and the molar mass, and that's not very useful. I mean, you can easily determine the molar mass from the structure here. Infrared spectroscopy, quite useless because it only tells us about the functional groups, and we know that there's chlorine already into it. It's not like going to help us. Is it a stereoisomer? Is it going to give us the chiral carbon? Like, does it? Yeah. C, high performance liquid chromatography. So HPLC, not very helpful because HPLC can be used both quantitatively, it's useless for quantity right now, but qualitatively, in terms of qualitatively, it tells us about no polar and polar, like how that's not very kind of useful in this case because we just want to find out, yeah, like if it's a stereoisomer. So it must be the nuclear magnetic resonance spectrum. Actually, there are two NMRs. You should know. There is the proton NMR, and there is hydrogen NMR, sorry, and there is carbon NMR. And this kind of help us because let's look at this and actually draw this in terms of how would it look if it's, we want to draw a chiral carbon with it. So it has to be C here, Cl here. Here we have this, a hydrogen here, and two C's here. Does that fit? So here is this carbon over here is chiral because it has two overall different side groups. It has a chlorine here, hydrogen here, a methyl group here, and an ethyl group here. So this is this overall carbon here is chiral. So, and the thing about the NMR, it tells us like the carbon environments, and in this case, how many carbon environments there are. There's 1, there's 2, there's 3, and there's 4. There should be 4 carbon environments. So that kind of tells us quite a lot about the spatial arrangements. Remember, stereoisomers, we're talking about the spatial arrangement, and NMR actually does help us with spatial arrangements. So that's beautiful. NMR hydrogen, so hydrogen NMR, so hydrogen environments. How many? Yes, it does tell us because, like for example, if we can see that for the carbon, there's supposed to only be 1 hydrogen in that carbon, and there's supposed to be 3, the other one 2, and there's another 3 here. So yeah, it's the most kind of helpful in determining the stereoisomer. Not too bad. I really do enjoy this kind of question here. Question 13. Which of the following statements about flashpoints is correct? So let's first define what a flashpoint is. It's pretty much like the lowest temperature at which a compound gives off sufficient vapor for ignition in air. It's like petrol, for example, they tell you in the petrol station, they tell you, hey, do not smoke. It's because, say you're putting petrol, and petrol, believe me, it has a very, mostly like the butane, ether, all those fuels, what they have is they have a very low, remember it is the lowest temperature, and they tend to have it in the negatives, and that's very dangerous. Like, let's say, I don't know, negative 30 degrees Celsius. And so if you put, for example, if you just put a spark, like when you're drinking a cigarette or something, not drinking, but smoking a cigarette, what happens is if even a spark hits that fuel, like a little fuel, because it's such a low temperature, it will generate, it will fire, it will burn quickly. Because yeah, that's what flashpoint is. I hope that kind of just gives you a little bit, yeah. It's like the lowest temperature at which the vapor ignites in air. So let's look at A. The flashpoint of butane is lower than 25. That's pretty much true. Butane is it's a fuel. So you should know that normally all fuels, if you don't know the flashpoints, they're always in the negatives. So, absolutely, I would say, yeah, the flashpoint of butane is lower than, of course it is, 25 degrees Celsius. So I'll put a tick on that. As flashpoint increases, the viscosity decreases. No, wrong. Flashpoint, the flashpoint, how do we determine flashpoint? It's all because of the carbon, how long the carbon chain. The higher the carbon chain, so the bigger the molecule is, the more the flashpoint increases. And also viscosity increases itself, because remember, viscosity is the rate of flow. So if you and it also depends on the carbon chain. Like the bigger the chain is, the higher the viscosity is. So both flashpoint, if the flashpoint increases, also the viscosity should have increased too. So yeah, wrong. C, the flashpoint of a compound is higher than, no it's not higher than its boiling point. That's rubbish. It's lower, it's very low, as we see. D, the flashpoint of butane is greater than the flashpoint of butane 1-ol. Wait, so butane is, okay, butane is greater, rubbish. We know that butane 1-ol has stronger intermolecular forces, and hence its structure is stronger, and hence it would have a higher flashpoint. Butane is much lower in case because it just has dispersion forces. So absolutely, butane 1-ol has a greater flashpoint. It's not butane. So easy. So A would be the best here. 13A. Alright, let's move on to the next question. Question 14. The following diagram represents the structure of a non-essential vitamin. What is non-essential? Non-essential means that we don't actually need it in the diet. We actually produce it. Our body naturally produces it. Normally, like vitamin D, our body normally produces it from the sun. Vitamin C is essential, from my knowledge, because like you have to take it from fruits, citrus, or yeah. Just a beautiful hint. Yeah, this vitamin is what? Okay, what do we see about the structure? So we can see this polar side here, and we can see this very non-polar side, and it's like 10 times of it. So imagine this here, non-polar side, 10 times of it. It's going to be a very, so highly, this whole molecule is highly non-polar, because it has a very long non-polar tail here, and it will go for like quite a 10 units of it. Yeah, so this vitamin is fat soluble. Yes, non-polar is fat soluble. Absolutely. Water soluble, rubbish. It's not water soluble. If it was water soluble, it would have been polar. If the molecule was highly polar, it would have been water soluble. So not B and D, because they say water soluble, so it's only fat soluble. Fat soluble and can be produced by the human body. Yes, as we said, it is non-essential, so it can be produced by the human body. Easy. Question 15. Aspartame has only what? 1 chiral center, 2 stereoisomers, 4 optical isomers, 3 structure. Let's have a look at the structure using our data book and really determine that. Let's have a look at aspartame. Here it is. Aspartame's over here. So it says 1 chiral center. Let's have a look at the chiral centers here. So there's going to be a chiral center here. Yes. Where else? That. Anyway. Wait, here also, yes, that, and that, and that. And that's it. There's actually 2 chiral centers. Not 1 chiral center, that's wrong. B, 2 stereoisomers. Remember, when we're talking about stereoisomer, it's both geometric and enantiomers, but in terms of this, it's not going to be geometric. There isn't a C double one. So when we need, it's only going to be optical isomers. And to know how many optical isomers there are, we would use the 2n rule, where n is the number of chiral carbons. And in this case, our aspartame has 2, so it'll be 2 to the power of 2, which has 4. So it would have 4 optical isomers. So it would have 4 stereoisomers. So B is wrong. C, 4 optical, beautiful, that's correct. And 3 structural isomers. Look, oh, absolutely, I have no idea, but for it, like, I'm looking at the structure, it has so much stuff. I don't even think there's going to be 3 structural isomers. There's going to be more than that. It's going to be like, I don't know, quite a lot, not just 3, yeah. So C would be the easiest, yeah. It's just beautiful. So C would be the answer for that one. 16. The number of carbon-to-carbon double bonds, so in a molecule, can be identified by reacting the molecule with hydrogen gas. The type of reaction involved is a addition reaction. Okay. 10 grams of a fatty acid becomes fully saturated. So, like, for example, unsaturated when they have a double bond and they react, and then it becomes, of course, saturated. After reacting with hydrogen gas, the fatty acid is what? Okay, so let's really have a look at a relationship here. So let's just draw, let's see how carbon to double bonds, what's the relationship between the carbon to double bonds and the hydrogen gas. So let's just draw the most basic. If we draw ethene here, so H, and we react it with hydrogen gas, So yeah, we only need 1 mole of hydrogen gas because there's going to be, when it reacts, yep, it's going to give us CC. It becomes saturated. All right, and it's going to have that. All right, so it becomes, okay. And what about if we have, because it's telling us that we want to find the relationship between the carbon-to-carbon double bonds and the hydrogen gas. So what about if we have, let's say, I don't know, like 2 double bonds now? What happens now? We're going to need, wait, so 1 here will be 1 here, so that will be 1, and also another 2 here. So there will be 2 H2s, and that's going to give me C, 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 and okay. Perfect. Okay, wait. I think I'm seeing a pattern here. So the number of double bonds, for example, in this case is 1, will give us a 1 coefficient. Like for the hydrogen gas, it'll be 1 mole of coefficient. For example, here we had 2 double bonds, and we had to use 2 hydrogen gas. Let me just, I want to make sure that's correct. Let's just use 3 now. CC, like that. 3 double bonds, and see if that also works. So we normally, the pattern here should be 3H2, and let's check if that works. We're going to need 1, 2, so that's going to be 1. We're going to need here and here. That's going to be 3 H2Os. Beautiful. Okay, I think I see the pattern. So the actual, what's happening is the number, the num of carbon-to-carbon double bonds is actually equal to the mole, the coefficient mole of hydrogen gas. And this here is going to give us the help that we need for this question, for calculations. Wow, it's actually quite hard. You have to look at patterns and stuff. All right. So the fatty acid is oleic acid. So, what did I do? Okay, so if we use oleic acid, what does oleic acid even look like? How many? So because we're only going to need, to be honest, we're only going to, okay, wait. First, let's determine, before we even do that, let's first determine the mole of this hydrogen gas. So the mole of hydrogen gas is what? It's the mass, which is 0.263 over 2, because there's 2 hydrogens, and so that'll give me this. 0.1315 mole. Easy. So, okay, and so we now have the mole of hydrogen gas, and it should be equal to, like, okay, so the number of carbon-to-carbon bonds. So, okay, let's draw oleic acid. So when we react oleic acid with hydrogen gas, remember the ratio. So let's go here. How many double bonds does oleic acid have? Oh, look at this. Oleic acid has only 1. So it's actually a 1-to-1 ratio here. Oleic acid, so it's a 1-to-1 ratio, so we're going to put a 1 here. And yeah, so if I had 10 grams, so 10 divided by the molar mass of oleic acid, which is 282, it should, because it's a 1-to-1 ratio, the mole of oleic acid should be equal to the mole of hydrogen gas, which is 0.035. It's not the same as this over here. It's actually, yeah, it's 0.035. It's not the same as that. So A is wrong. Let's try the other ones. Now the next one is this one. So linolenic acid plus hydrogen. But how many moles of hydrogen gas do we need? Let's just check. How many double bonds does linolenic acid have? Linolenic. This one, and it has 3. Okay, so it has 3 what we call double bonds. So it'll be 3 here. There'll be 3 hydrogen gas, and so let's have a look at that. Again, same thing. We're gonna do 10 grams of linoleic acid. React because the mole mass is 278, and that's gonna give us the mole of linoleic acid. So 10 divided by 278, and that gives me 0.0359, and because we want to because it's the mole ratio of hydrogen gas is what? To get that, it's like multiplying it. So, wait, linoleic acid. We need to multiply this by 3 to get the mole of hydrogen gas by coefficient. So, and that's going to give me 0.1079. And it's not the same as our answer. So, B is also wrong. Let's try again for the next one. Archidic acid. So I just want to check how many double bonds that has. Archidic acid. It has no double bonds. So that's wrong, absolutely. So D must be your answer. Let's just double check D if it's correct. D is what? Archidonic. And it has how many double bonds? It has 3 here and it has 4. So 4 in total. So it has 4 double bonds. So it would be like arachidonic acid. Because it has 4 double bonds, we know that the number of double bonds is equal to the mole ratio of coefficient. So plus 4 hydrogen gas. So also H2 for hydrogen gas. So it will be 10 divided by 304. And that's going to give you the mole of arachidonic acid. So 304. And I got that. And now I'm going to get the mole ratio of hydrogen gas, I'm going to need to multiply it by 4 over 1. Because to get, so times 4. And that gives me, 0.1315. Beautiful, the same mole ratio as that. So D is absolutely your answer. Can I be honest, this question is quite hard, I'm not like, it's finding the relationship between them. So I think a lot of students will struggle with this question. So yeah, I hope that little bit makes sense. Question 17. The tradition of bronzing baby shoes dates back for generations. Before electroplating, the shoe is painted with a conductive material. The copper Cu electrode and the copper sulfate solution cell was used for electroplating a shoe as shown. And you should always know, one of the hints that I love when I look at electroplating is, what's the thing that's been electroplated? It's actually this shoe. And the shoe, because it's been electroplated, it's always going to be the reduction side. That is a hint. And so it's going to go reduction, and hence it's going to be the cathode. So this hence must be the oxidation side. And so it must be the anode. And we know that the oxidation for the anode is actually the positive, and for the cathode it's negative, because it's an electrolysis. And so again, the thing that gives you the hint is actually look at this. This is positive and this is negative, because this is shorter and this is bigger. Also, that can give you that hint. And yeah, that's the most. I always try to, when I do an exam, I always try to detail my things so it makes my question easier. During the electroplating process, the copper electrode is oxidized. The copper electrode is oxidized. Yes, it is, as we are showing here. This is your copper electrode. And its mass is unchanging. Wrong. The mass will decrease because, remember, what is that current flow? It's going here. It's from positive to negative. Hence, this one here is going to be increasing and this one's going to be decreasing. So it's not, the mass is going to be decreasing. B, the shoe is coated with copper metal. So the shoe is coated with copper metal at the cathode. Okay, that's correct. It is, the shoe is going to be coated with copper metal. And at the cathode. That's where it is. So I'm going to put a tick at that. The copper electrode is the copper electrode is the oxidation. So it's the one it's the reducing one, the oxidation agent, which is wrong. It's the oxidation one. So D, oxygen is produced at the cathode. What does oxygen got to do with this? Actually, oxygen can, because it's aqueous. Wait. I want to make sure I fully grasp this. Am I making a mistake here? Did I fully forget it was aqueous? Let me have a look at this. So I know copper. Have a look at this. So copper is where? Copper is here and here. So when we're saying aqueous, means that water is actually here. We're going to have water from here and water from here. And this is actually quite useless, because still the strongest reduced oxidant in this case is still the Cu2 plus, and the strongest reductant is the Cu solid. So still there is no reaction with the water, so that's still good. I'm still happy with that. Yeah, that you had to make sure you check that. When I saw oxygen, I'm like, shit, did I fully forget about the aqueous? Yeah. So B must be your answer for that one, is it? Yeah. Yes, that's pretty much good. 18. Which of the following galvanic cells will produce the largest cell voltage under a standard laboratory condition? Easy. What a beautiful question. Let's check that. So we have zinc, and we have nickel 2+, and zinc 2+. Let's go look at that in our electrochemical series. I'm just going to rub these out because I don't want them to confuse us. We have zinc. Where's zinc? Zinc's over here, which is this one over here. What about nickel? Nickel's over here. So it's going to be negative 0.25 minus negative 0.76. That's going to be equal to... That's 0.51 volts. Next one, have a look at the next one. So we have Fe2+, and we have platinum, so it doesn't, and we have hydrochloric acid, which is just a plus that we need. That's going to be reacting. So H+, where is that? H+, I know for a fact H+ is 0, but where is it? It's over here, so it's 0, and Fe2+, which is this one over here. So it'll be 0, okay, it's just 0.4 from the thing, 0.44 volts. Next one is, this one's Ag+ and Cu2+. Let's have a look at this one. Ag+, that's here, and Cu2+ is over here. 0.8 minus 0.34. Minus 0.34, that gives you 0.46 volts. Next one, we have Sn2+, and we have platinum with pure water. That's rubbish. There's not going to be a reaction because it has pure water and inert electrodes. So there's no cell voltage going to be produced in that one. So the one that has the highest is A. Easy. Alright, let's go to 19. Lactose is commonly found in milk and milk products. The enzyme used to hydrolyze lactose in the human small intestine is lactase. One of the best hints I can give you in chemistry is when you look at for example, let's say we don't have lactose. It's the enzyme that we actually lack. It always starts with the same, but it always has the ACE in there. So, for example, cellulose, we lack that, and so what enzyme do we lack? We lack the enzyme cellulase. It's always the ACE. So that's the beautiful hint I can give you for future. Lactose intolerance describes the limited ability of humans to hydrolyze lactose. Consider the statements. Statement 1. Lactose intolerant people produce too much lactase enzyme. Rubbish. They don't actually produce a lot. They don't even produce because that's why they can't actually drink milk and stuff that have lactose or dairy products. So 1 is wrong. 2. Insufficient lactase leads to some lactose not undergoing hydrolysis in the human body. Yes, absolutely. Lactase is needed for the hydrolysis of lactose, and if we don't have a lot of it, there is going to be some that do not actually go through hydrolysis. So I'll put a circle on that. That looks good. 3. Lactose intolerant people can add lactase drops to milk to help digestion. Yes, absolutely. If I add lactase, that then will help break down lactose and hence they can digest it. So 3 looks good. 4. Lactase assists in the hydrolysis of lactose. Lactase assists in the hydrolysis of lactose into 2 glucose molecules. I know lactase is in our thing. Where is it? Lactose. Let's see. Is it 2 glucose? If I'm not mistaken. I want to double check. Here, lactose, alpha galactose. So this one here is a glucose. No. The other one is a galactose, I think so. Yeah, galactose. Yeah, they're not the same. Be careful, they're not. You should know that this one over here they're not the same. Like glucose. This one has an upwards oxygen, so it would have had an OH here, and this one has a downwards OH. And so this one looks like, this one over here looks like the glucose, and this one would have had to be the galactose. With the, I think it was galactose. Yeah, pretty much. That's it. So 4 would be wrong. 2 and 3. C. Easy. Question 20. The oxidation of sulfur dioxide, SO2, to sulfur trioxide can be represented by these following equations. Beautiful. So we have the Kc value and the temperature. Our equilibrium mixture, so our equilibrium has a concentration of 0.12 this and 0.16 oxygen. The temperature of container is still 1000, great. The equilibrium concentration of SO3 at 1000 degrees Celsius is what? Easy. So let's first find the Kc value. It's going to be the product, so SO3 squared, because it has the coefficient 2, and it'll be oxygen, and it'll be SO2 squared, because it has that coefficient. So, and that we know that already that Kc value is what? We know that Kc value is 1.75 from the equation, and we're trying to find SO3. So, but we already know that oxygen, this one, let me rub that off, is 0.16. And SO2, this one here, is 0.12, and it's going to be squared. So, let's do some algebra here. 1.75 times 0.16, 0.12 squared, and it's going to give me 0.0040 this, and then we have to square it. So to get the concentration of SO3, which is 0.063. This, so which one looks like that? Looks like these, your answer, the only one that has 6.3. And yeah, -2. Beautiful. Next question. Question 21. The diagram below represents the Maxwell-Boltzmann distribution of an uncatalyzed reaction. The effects of adding a catalyst could be what? So what happens when you add a catalyst? We know that when adding a catalyst, we actually decrease the activation energy. And imagine this is your activation energy initially, as we see. And so the area here means like the amount of atoms or that have sufficient energy to overcome that energy, activation energy, hence react. So if we decrease the activation energy, so imagine now it's over here, what happens? There is a bigger area. There's actually a bigger area for of more atoms. So there's a more proportion of atoms that are able to react and hence go above and beyond the activation energy. Easy. So the effects of adding a catalyst could be the curve flattens to reflect the lower activation. No, the curve doesn't flatten. The curve only flattens when you decrease when you start increasing temperature, sorry. So when you affect temperature, that's when the curve flattens, and yeah, so 2, the curve shifts to the right, absolutely not. And the EA, so activation, shifts to the left. Yes, as we saw, we shifted it to the left. So 3 looks, only 3 is your answer there. Easy. Question 22. Which of the following statements about conducting an experiment is the most precise? Or the most correct, sorry. Precise results may be biased. Yeah, that could be true because, for example, you can, let's say you go and you want to detect the result of a pond, the concentration of bonds, I don't know, something, like you want to take the concentration of the, in the pond, you want to take the concentration of something in the pond. And so you go on and the bad day, you accidentally, let's say it's not the best temperature, there's a lot of fungus and stuff, there's just a lot of bad stuff. You go and you take your data and stuff, and guess what? You do it and you analyze it, and guess what? Of course, it's going to be, the data will be precise. Precision doesn't mean it's accurate. Precision means the values are very closely related to each other. And of course, they would be very closely related with each other. But does that reflect the accuracy of the real concentration of the bond? No, it doesn't. Because you could have went on a bad day, and let's say the average good day would have, you didn't accidentally go there. So yeah, precise results may be biased because absolutely, so precise result may be biased. I hope that kind of makes sense. B, accuracy is assured if sensitive instruments are used. Look, accuracy does increase when sensitive instruments are used because we decrease systematic errors, but it's not it's not like you cannot assure accuracy because there are going to be some fluctuations, like maybe some environmental fluctuations that you can have, something. Yeah, it's not 100% accurate. You cannot assure accuracy, so that's rubbish. 22. A method is valid. Oh, sorry, why did I put an X on this one? Precision. I'm supposed to put a tick on that, sorry. Precise results may be biased. True, they are, yes, that's what we were talking about. They can be biased because it really depends. Yeah, you could have took them in a bad day, and guess what? They can be precise, but they are not the proper values. See, a method is valid if it identifies all control variables. No, remember, a method is valid if it, correctly answers the aim, the hypothesis, mostly the hypothesis, because the hypothesis has the independent and dependent variables, so it answers the question. So not just the control variable. So C is wrong. D, repeating a procedure will remove uncertainty of the result. Look, repeating a procedure will remove the random error, but for example, if let's say you had 7 students using the same, I don't know, thing to measure mass. I fully forgot what it is. The weight scale, and they're using, it's not calibrated properly, so not calibrated, but it's like there is some uncertainty into it, and so all of them use it to measure their values. And guess what? They could they've repeated the same experiment, but guess what? Yes, they may have got all the same values, but guess what? That's not like removing the uncertainty. It doesn't remove any uncertainty. So repeating would remove the uncertainty of the result. Yeah. So that all of them could have the same result, but those results could be wrong because there's systematic error in the scale. So D is also wrong. A is the best one here. Precise results may be biased. Yeah, that was good. 23. Which of the following statements about enthalpy change is correct? Okay, the sign of the enthalpy change for an endothermic reaction is negative. No, you should know that the enthalpy change for a endothermic is always greater than 0, so it's always positive. B, the sign of the enthalpy change for the condensation of a gas to a liquid is negative. Well, the way that I would actually answer this question is, if you don't remember, if you did units 1 and 2, you would know, for example, if this is your energy, and say this is temperature. So we know, like, this is the fusion and this is vaporization of water, let's for example say. And so this is this is 0 degrees Celsius and this is 100 degrees because it boils at that point. So we know when we're going from, example, liquid to gas of water, what are we doing? So we're going from when we're converting it to all liquid to gas, we're actually consuming a lot of energy, and when we consume energy, that is what we call endothermic. So the question here tells us the sign of the temperature change for the condensation of gas to liquid. We're going the opposite, so it has to be exothermic. So that could be right. C, the enthalpy change is the difference between the activation energy and the energy of the reactants. Rubbish. We know that the enthalpy change is the difference between the energy of the products minus the energy of the reactants. So C is wrong. Let me take that off. D, the enthalpy change is the difference between the activation energy and the energy of the products. No, it's the energy of the products minus the energy of the reactants. Nothing got to do with activation energy. So B is your answer for that one. 24. The diagram below shows an electroplating cell. So great. The cell contains 1 liter of an electroplating solution. The electroplating cell is run for 1 hour and 3 amps. Which one of the following electroplating solution will deposit the largest mass of metal onto the object? This is actually kind of a repeating question. I've seen it quite a lot in exams now. There's a lot of calculations. That's why I don't like this question, but they're not too bad. So what we need to look at is, okay, we know for a fact we need to find the charge, and the charge is the current times the time, and the current is 3 amps times the time, which is 1 hour, which is we need to convert it to seconds, so it's 1 times 60 times 60, which is what? Which is 10800 coulombs, and so we can actually calculate the number of moles of electrons by we know that the charge over the Faraday's constant, which is 10800 over 96500. So let's put that there. that's going to give me 0.1119 mole. Okay, that's gonna that's good. So we have that. So let's have a look at the first option. So if we use Ag, so silver, so let's write that down. So Ag plus E minus Ag solid. So we want to see how much Ag solid we can produce. If I know the number of the moles of electrons, because it's a 1-to-1 ratio, it will be the same as the number of mole of Ag solid silver, and hence we can easily find the mass that will be deposited, which is 0.1119 times the molar mass of Ag. And I'm actually going to find the molar mass of all of them, so I don't have to go back and forth with this. So Ag is what? Let's go here. Ag, where is A? Oh my god, I have to turn my head here. Ag, where are you? 107.9. So 107.9. Let me find the other ones also. So we need cadmium too for the future question. Cadmium, where is cadmium? 112.4. So 112.4. That's for CD. For PB. So PB, where is that? Wow, it's really hard to find these. Why am I struggling so much? I mean, PB is 207.2. And we also need aluminium. So aluminium will be 27. Easy. We've got all the molar masses. And yeah, we just keep doing the same thing and see which one has the greatest mass. So let me just, multiply that by 107.9. And that's going to give me 12 grams. So the first one, is going to give me 12 grams of Ag. We'll deposit 12 grams of silver. Next one, cadmium. So same thing. We write so cadmium 2 plus 2E minus goes to cadmium solid. And so, to find the mole of cadmium, it's going to be the mole of the electrons times what? So we're going from cadmium. So we're going from electrons to cadmium, which is timesing it by a half. So 0.1119 times 0.5. So we got that, which is 0.05595 mole. And then we want to find the mass of cadmium, which is going to be multiplying that by the molar mass of cadmium, which we said was 112.4. 112.4, and that's going to give me 6.3 grams. So 6.3 grams for this one. Let's try PB also. PB2 plus 2E minus goes to PB solid. Hence, it's going to be the same thing. So the number of moles of PB solid is just going to be equal to 0.119 times half. So times half, which is 119 times 0.5. That's going to give me this 95 mole. And then the mass of PB solid is just multiplying that by PB, the molar mass, so which is 207.2, which is pretty much approximately 11.6 grams. That's done with that. 11.6 grams, and the last one is aluminium. So aluminium, 3 plus 3E goes to aluminium solid. All right. So the number of moles of aluminium solid is going to be the electrons, which is 0.1119 times 1/3. So 0.119 times 1/3. It's going to give me 0.0373 mole. Hence the mass of aluminium is going to be 0.0373 373 times 27, which is 1 gram. Wow. So yeah, that's just 1 gram. So the one that has the highest mass deposited is A. Easy. That took very long, I'm going to be honest. That, yeah. 25. The following concentration time graph refers to a mixture of three gases, P, Q, and R, in an enclosed 5-liter container. At time T1, the mixture is heated. Alright, the equilibrium system that represents the graph is what? Okay, I've seen this kind of question so many times in those past exams that I've done, and it's one of the most nicest. So you want to just pick one randomly. Let's pick the first one. So P goes to 2Q goes to R, so it's an exothermic reaction. And what do we know about exothermic reaction? Let me write the equation. Goes to that. Oops, that's ugly. (2Q plus R), and it's exothermic, so energy will be released on the right, and hence if we're increasing temperature, so imagine we have so much temperature, what the reaction is going to do is going to be, oh, I need to go backwards to compensate for that. Okay, so if it's going to go backwards, we're going to be increasing P. P will be increasing. Yes, P is increasing here, and hence Q and R will be decreasing, but Q will be decreasing twice because it has 2 moles of that. And yes, it is actually increasing twice with the amount, whereas R is increasing the same rate as P, but in the opposite. So yeah, looks like A actually does fit the answer here. D is just the same equation, but it's endothermic. So if it was endothermic, the energy will be on the left side. And so if you increase the temperature of the energy, because when you increase temperature means you increase energy, the reaction is going to be, oh my god, that's so much energy. How am I going to get rid of that? I'm going to go react to the right. And if it reacts to the right, we're going to be going to be creating 2Q and R, which in this case, Q and R are decreasing. We're not actually, the concentration is not increasing. So yeah, A is the one here. That was beautiful. Not a bad question. 26. The calibration factor of a bump calorimeter was determined by connecting the calorimeter to a power supply. The calibration was done using 100 milliliters of water, 6.5 volts, and a current of 3.6 amps for 4 minutes. The temperature was of the water increased by 0.48 during the calibration. Okay, so we can easily calculate the calibration factor of this thing here. So 4.2 grams of sucrose underwent complete combustion in the bump calorimeter. The temperature of the 100 milliliter of water increased from 19.6 to 25.8. We have the molar mass of sucrose, the experimental heat combustion of pure sucrose in joules per gram. Joules per gram, that's what we want. So, okay, first actually let's calculate the calibration factor. So calibration factor is, we know it's volt times the current times the time over the change in temperature. And we know what's that. So we know the voltage is 6.5, current is 3.6, minutes 4 times 60 because we want it in seconds, all divided by time. All divided by temperature, my apologies, which is in this case 0.48. Let's see what that gives us. 6.5, 3.6, 4 times 60, 0.48. So that gives me, let me rub all this out, this part here. What's our calibration factor? It is going to be 11700 joules, joules per degree Celsius, negative to the negative. Yep. Now the next question says, okay, if we have 4.2 grams of sucrose underwent complete combustion, the temperature of the water increased from this. Easy. So what we can actually find the energy by what? By multiplying the calibration factor, which is 11700, by what? We multiply by the temperature change, which we said was this. And we can find the energy. 25.8 minus 19.6. So that 20.8 minus 9.6. And that's going to give me 72540 joules. And so we have the joules, and we just need to divide it by the mass to get joules per gram. So to get the heat combustion, it's going to be 72540 divided by 4.20, which is going to give me 4.20. That gives me 17271. Yeah, joules per gram, which is what? Looks like C is your answer for that one. Yep, is it 1, 2, 3, 4? Yes, it does. 26C. 27. An organic compound has a molar mass of 88 grams per. So molar mass of that. The carbon NMR spectrum of organic compound shows that there are 4 distinct peaks, so it means that it has 4 carbon environments, pretty much. Easy. I'm going to write environments. I'm not going to, yeah, environments. And so the organic compound is most likely to be what? Let's look at butane 1-ol. So let's draw that. Butane means 4 carbons and OH here. Looks like this. All right. So first let's check if its molar mass is 88. So we have 4 carbons, which is this, plus 1 oxygen, which is 16, plus 4, we have 10 hydrogens. Yeah, so that's going to give me 4 times 12 plus 16 plus 10, and that gives me 74. It's not 88, so that's wrong. It's not going to be this one. Let's check the next ones. Next one is butane 1 also. So 2-methyl butane 1 also. Butane, we draw butane and 1 OH here. And at 2, we have a methyl group, this thing here. Like that. And so, how many carbons we have? Now 5 carbons. We have oxygens, and we have, how many hydrogens? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. Let's see what's that equal to. 4 times 12 plus 16 plus 12. That's going to give me 88, so that's good. Could be that one. So we just need to check if it has 4 different carbon environments. So 4 carbon environments. Well, let's look. We have 1 here, 2 here, 3, 4, and 5. There is no symmetries, yeah, so there's 5 actually. Yep, so there's 5. We don't have 4 in this one, so that's also wrong. Next one. So 2-methyl butane 2-1-ol. So we draw butane. At 2 we have a OH. And at 2 we also have a methyl, so like this. Alright, actually we can redraw this nicer like this. So to make it like more symmetrical, this one looks OH. We can draw an OH here. And that C, H can be here. So, it can be redrawn like that nicer. Now, what can we see here? So, by the way, you should know that also this one is the same. It has 80, the molar mass of 88 because it's pretty much the same number of like some number of atoms. So it's going to be 88. It was the same as this one, but yeah. And so, what do we have? So how many carbon environments? Well, because there's symmetry, like in this carbon, as you can see, because of this and this, they're symmetrical. We consider this one fully 1. These 2, we fully consider them as 1 because they're symmetrical. So that's 1, that's 2, that's 3, and there's 4. Beautiful. So we have 4, and also it should it's the same number of atoms as the second one. So as we found, it was 88 grams per mole. So great. It looks like C is the answer for that one. Let's have a look at 22. So 22, the connection of all gases in the equilibrium reactions below is 1 mole. Okay, so all the gases, the concentration. Okay, in which reaction does the Kc value be this? Well, if it's quite hard to determine because, like, for example, if you write the Kc value for this, H2 to the power 4, CO2, H2O squared, CH4, like, because they have all one, like it's quite useful, this number, because they all have the same Kc value in what way what I mean, because like if I all have 1 mole of concentration, so this hydrogen will be 1 to the power 4 times 1 squared times 1. It's just going to be all equal to 1. Even the same, 1, 1, 1. All the Kc values are going to be 1. So that's not going to help us. But you know what's going to help us? It's that unit. For example, well, if I'm writing the Kc value of this, the first one, which is, again, let me write a H. Actually, let me just get this back. It's easy to get the Kc value because we know H2 to the power 4 is m to the power 4 times m over m squared times m. So we can cancel those out. So hence it's m squared, which is not m to the negative 2. So it's not a reaction 1. Look, the fastest way, I will teach you a trick. Now, yes, you have to write the equation and writing that m squared. It just takes a lot of time. But what about if I told you there's a quick way? And the quickest way that the quickest way is doing this. First, to find the unit, the quickest way is to do this first. So what is the coefficient? What's the total on the product side? What's the total number of coefficient? So for example, this one has 1 and this has 4, so we add them up, it's 5. What's the total number of coefficients here? It has a 1 here and there's 2 here, so it'll be 3. So now always, what's 5 minus 3? It's 2. So it's going to m to the power m, it's always going to be, of course, m. Because it has 2, it's going to put a 2 on top. And that's here. It's always products minus the reactants. Let's try it for the other ones too. The next one is this one. So what's the total number? It's actually 2. The total number here is 3 plus 1, which is 4. What's 2 minus 4? Negative 2. Aha! So it's probably reaction 1 because that's m negative 2. Beautiful. What about the other one? Let's rub this out. Let's check the other ones quickly. So this one is, of course, it's a 2. And this one is also a 2. So 2 minus 2 is 0. So it'll be m to the power 0, which is just nothing. Not those. Next one. 1. 1 minus 2, negative 1. So it'll be m negative 1. Quite useless, to be honest. So the only possible answer is 2. Easy. Question 29 and 30. So using the following information to answer question 29 and 30. The concentration of vitamin C in a filtered sample of grapefruit juice was determined by titrating the juice with 9.367 times 10 to the power 4. Okay. Mole of iodine. So we have the concentration. Solution using starch solution as an indicator. The molar mass of vitamin C is this. The reaction can be represented by this following equation. Alright, so this is your vitamin C, and then it's reacting with iodine, of course, and yeah, this is the reaction. The following method was used. Wet a clean 250 milliliter conical flask using a 10 milliliter measuring cylinder to measure 5 milliliters of grapefruit juice into the conical flask and re-weight it. Add 20 milliliters of deionized water to the conical flask. Okay, makes sense. Adds a drop of starch solution to the conical flask. Titrate the diluted grapefruit juice against the iodine solution. Yeah, makes all sense. Let's look at the questions. 29. Which one of the following errors would result in an underestimation of the concentration of vitamin C in the grapefruit juice? So an underestimation. So we want to look like underestimation. Let's check the first option. 90 milliliters of deionized water was added to the conical flask. You should know that adding deionized water to the conical flask, it does not affect it. Be careful. That's why, it's diluting the when we're diluting the actual vitamin C, when we dilute it, it doesn't really. You should know that it doesn't actually affect the concentration, because what we have is then after we'll have a what do we call it again? I fully forgot. Yeah, so 90 milliliters of deionized was added to the conical flask. We should always know, when we put water, when we dilute the, for example, the grapefruit to get vitamin C, we can dilute it. It doesn't really affect the concentration. Because at the end of the calculation, we times it by the dilution factor, and hence we get the answer. So it really doesn't even affect anything, to be honest. B, the concentration of I2 solution was actually 9.178. So we used this one. So we've actually gone over the concentration of iodine. So, okay. So let's think about this. So this was the true value, but we've like we've said that it had a higher concentration. So let's look. So we know that N is equal to CV, and so we know that, let's say the volume let's say the volume is constant. So if we, for example, this one, the concentration is high. So imagine this is high, meaning that the number of mole of iodine is high because it's a 1-to-1 ratio. These two, it means also that the number of mole of like the vitamin C is also high. And so when we're calculating the concentration, which is number of mole of N over V over C, if we would know that the N value is very high, what happens to the concentration of vitamin C? It's also going to be high. So it's going to be an overestimation, not an underestimation. So B is wrong. C, the initial volume of iodine solution in the burette was 1.5 milliliters, but it was read as 2.5. Okay, so let's really think about this one. So if I had the burette, let me just draw like this long tube. Think if it's a burette. If the initial volume of the burette was actually 1.5, but it was read as that. So imagine this was the solution, yeah? And so this here is that 1.5 milliliters. And so let's say this is the concentration, of course, is this. And yes, we have all these molecules of iodine. And so if we increase the volume, like we've accidentally read it to 2.5, so here, let's call this 2.5, what have we done? We've done a big mistake because the concentration hasn't changed, but we've increased the volume. Hence, like, if the volume has increased, what happens to the concentration? It's very low. The concentration of the iodine actually decreases because we've used a higher volume, but the concentration is the same. So if the concentration has decreased in this case, what happens? So imagine decreasing the concentration, hence will decrease the number of moles because it's a 1-to-1 ratio. When we're looking at the vitamin C, if the number of moles decreases, this number decreases, concentration should decrease. So it's going to be, and it's going to be a what we call an underestimation. So D, the balance was faulty and the measured mass of the grapefruit was lower than the actual mass. Wait, the balance was faulty and the measured mass of the grapefruit was lower than the actual mass. Wait, if we're assuming that the concentration is constant, it wouldn't really have an effect. I don't think D is wrong. Yeah, so like, for example, what's the difference between taking a, I don't know, like 2 liter, let's think about it. Like, let's say a 2 liter juice and the concentration is like constant. Because let's say the concentration is, I don't know, some 20. And even using a little like sample, it will still have the same concentration. So it really doesn't affect concentration. D is wrong. Like having a wrong mass of grapefruit was, yeah. Wait, the balance was faulty and the measured mass of the grapefruit. Yeah, when we're talking about mass, yeah, the measured mass of the grapefruit juice was lower than the actual mass. Yeah, is that right or wrong? That's actually quite... The balance... Yeah, because normally the measured mass of the grapefruit was lower. Like, even taking a lower mass, it's just, yeah, it wouldn't really affect it. So I would say C is the answer. I have to look at D, to be honest. D is actually quite confusing me. But yeah, C looks good. C looks very good. 30? Let's have a look at 30. Last question, 30. If the measured mass of the grapefruit was 4.9 grams and the titer was 21.5 milliliters, what was the measured percentage mass by mass concentration of vitamin C in the grapefruit? A very nice and easy question. Now, this is just telling us what to do. It means mass over the mass times, like what is it? The mass that we actually measured, which in this case, the measured mass, which was 4.9, and the actual mass that we got, which we'll calculate, times it by 100 to get the percentage. So this is mass, and this is also another mass. Yep. Well, how do we get the other mass? The theoretical mass. Well, easy, because if I know that the average titer was this, and so we know that the number of moles of iodine is going to be the titer 5.0 times 10 to the negative 3, which is the volume times the concentration, which in this case is 9.367. 367 times 10 to the negative 4, and we multiply those together. It's going to give me 0, it's a very, okay, wait, I'm just going to write it in a scientific notation, then 2.01 times 10 to the negative, so 1, 2, 3, 4, 5, negative 5. So that's going to be mole. Because it's a 1-to-1 mole, this would be the same as the, the vitamin C, which is C6H8, oxygen 6. And so we need to then just get the mass. And so to get the mass, but that'll be the same. So to get the mass of that, it's just going to be the number of moles, which is 2.01 times 10 to the negative 5 times by the molar mass, which they gave it to us, which was 176. Easy. Times 176. And that gives me 0.0035 grams. And so let's put that here, 0.0035 grams. And so let me rub all this out. Now, putting this as a percentage, so 4.9 times by 100, that gives me 0.072. B is your answer as a percentage. Easy. And that's it. I hope you guys learned something through this video. I need to double check 29 because 21 actually is confusing. So yeah, I hope I haven't got that one wrong, but I'll check it. And yeah, I hope you learned something through this video. If you guys want more of these videos, please make sure to like and subscribe, and yeah, share this video with your friends and classmates. Have a great day, guys, and take care of yourselves. Bye bye.